Oh man, we are outside Minneapolis at the Stratasys headquarters. A lot of you guys know who Stratasys is, but I don't know if you guys truly understand the level. When it comes to high level companies, Stratasys is on that top level. They've been around for 35 years and they put over $100 million per year into R&D. Not only that, when you look at additive, you don't think precision. And yet what they're doing in this building right here is going to blow your mind. They are AS9100 certified, they're ISO certified, they're working with the top companies in the world making crazy components, from fixturing to drones, aerospace, medical, dental, you name it, they're in it. Let's go check out Stratasys, baby. Boom.
So we have here is our PolyJet technology. It's another technology using photopolymer resins. What makes this one unique and different is the fact that we're actually 3D printing in color. It has the aesthetics of the final product itself. This technology also can be used then to produce human-like anatomy. So not only does it look like the human anatomy, if you touch and you feel that, you can feel the gum tissue.
Oh, that's crazy.
Feels like the actual gum tissue, exactly. This is actually the density, while it's a scale model of the brain tissue. So we can emulate the human anatomy well enough that surgeons can practice not on us, the patients, but on 3D printed models. PolyJet technology is used at Sick Kids Hospital. They specialize in complex cardiovascular surgery for pediatrics or children. And 3D printed models are a key tool for them to help their surgeons practice. So it has profound impact on the quality of life and the survivability of very challenging surgeries for young kids.
That's incredible.
So the process to make an eye, let's say you need a prosthetic for your left eye, to get it to match your right eye, it's a crazy artisan process, right? This technology now, you can take a scan of the good eye and then use that as the basis to 3D print the prosthetic eye.
The depth in it, you can see the layers.
Lifelike, right?
Yeah.
So what I have here is stereolithography. This is one of the longest running technologies in the industry, very stable, also producing parts in photopolymer based materials. So there's a vat of liquid resin here. There's an ultraviolet laser that touches the surface and solidifies the layer. And then the next layer is drawn, the next layer is drawn, it repeats that process. Really good aesthetics and feature detail, but here it's chosen when the size of the part is larger than a shoebox.
Very cool.
Now these are very small pieces of impellers or blades that would go into a turbine engine. This is the part coming directly out of the 3D printer, right? So it's a clear resin that is optimized for the investment casting process. So this is a piece of an investment casting pattern, it'll be a whole wheel. So it's coated in ceramic, resin powder to build up a shell. That shell's heated up, the pattern is burnt out. You're left with a cavity, and now you can pour the metal of your choice into that cavity. So this is a digital light projection based 3D printing technology. So like all 3D printing technologies, it's producing a part layer by layer by layer. So the inputs for our systems are photopolymer resins. So these are liquid materials until ultraviolet light touches them and then they turn solid. What makes these DLP, or what we call our P3 printers, unique is the capability in the aesthetic. So we're getting closer and closer to true injection molded surface finish. This is how the parts come directly out of the system. The part is being pulled out of the resin or printed upside down. Once a part comes out of the system, you manually rip the part away from the support structures, and then it's UV cured, and then you've got your usable part, or in this instance, a small production part of a little camera. Additive manufacturing, for the most part, has a lot less waste in comparison to CNC machinery.
Is there any recycling?
For our thermoplastic-based materials and our powder-based materials, you can recycle those. And we have a company that comes and gathers our waste thermoplastic. They take that, and for the most part, it's turned into composite decking and outdoor furniture is how they upcycle that material.
So this is Stratasys direct manufacturing. We've got over 100 printers running in here today. That allows us to offer an outsource for demand. We are the parts manufacturing arm of Stratasys. So we're using the printers to produce the end use parts.
You do that as like a job shop type, or is that for customers that are buying your printers, so you're pre-qualifying it with your parts?
It's both. Yeah, okay. It really is both. So 80 of our top 100 customers are Stratasys printer owners today. So they're using Stratasys Direct for outsourcing overflow, for running complex materials, for design help and being able to run complex geometries. This kind of gives you the depth of how packed we can get them in, right? Like any manufacturing floor, we've got our job board, so we're able to see capacity. So on the left side is every printer that we have. There's a lot more than that. You can scroll up and down, but this shows the schedule of all the builds. The greens is everything that's scheduled out. So this is just today. Gives you an idea of how busy we are. Every printer's got to run.
I mean, the certifications that you guys have and the strict documentation and all of it. I mean, you guys are super high level.
That's what separates us from other shops, right? This isn't hobbyist printing. This is end-use production parts that are going into aerospace applications, defense contracts that are end-use. We're not just printing parts and throwing them in a box and shipping them out. We call that strip and ships. Where our value comes in is in the contract manufacturing side of a lot of the post-processing. We continue to push the limit on dimensional accuracy, so we're CNCing parts to get to those dimensions where we can. We're hand finishing parts, we're sanding parts, we're putting coatings on, different paints that may be needed. So this is where you'd see the labor come into the work, so actually hand finishing, producing those high quality end-use parts. They're doing things like putting in heated inserts, sanding and finishing parts. They're also doing QC measurements to make sure that we're actually have printed what can meet those tolerances.
You guys have CMMs and stuff, or
We
how do
do.
they do the measurement?
Usual hand tools for measurements right now.
Okay.
The next group is our QC that is using CMM, ferro arms. The next future evolution for us is moving to more advancement into automation in those finished parts so that we can speed up that throughput. We're not using a small build envelope. These are big parts. We're talking 36-inch by 24-inch parts, bonded together to get really big parts. We've worked on recently some DOE projects for wind and energy. So can we 3D print wings that are going on a huge wind turbine?
Yeah.
And how are they handling the stress of constantly spinning around, lightning strikes, what does that look like? We're printing very strong features in small parts and bonding those together to get the length needed.
You guys do like pull tests and different tests on the materials too?
We
like,
do. Yep. Tensile stress tests, so stretch, twist. There's a lot of different testing.
Yeah.
One of the areas we've specialized in is actually in the front end of the design of the parts, qualifying our materials to fulfill certain applications. So it's written into that customer spec to use a Stratasys material on this Stratasys machine. And now we're running production parts that have to consistently be re-qualified to ensure we're staying within means to hit those specifications. It's on-demand printing. We get a request and within 3 days we can have parts at their door. We have machines here that are some of the first 900s that were ever made that are still running production. They're over 20 years old and they're beasts. I like to stop here too because these machines behind you actually are the Fortis 400 series. These are old machines, same type of thing. They're still running and not a whole lot has changed with these. These are still in high demand. They still are very efficient. They keep running. This is the newest, baddest machine we have, the F3300. These machines are producing what that 900 can in half the time.
Half the time.
They have the monitors, they have the sensoring that's needed to know when are they gonna break down, are we gonna have print failures, and it's alerting our operators that, hey, there's something going on here. So now a machine technician will come over, investigate the issue and say, we gotta stop this build, or we can keep running this build, but we're gonna have to replace something before our next print.
You guys have been doing this for so long now. You guys have all the supporting data. So if you have a customer out there that's like, wait, I might be able to do my parts, what would be the best way for them to actually hook up with Stratasys to see if they could do it or not do it?
Through our website is contact an engineer. You can get connected to one of our engineers that will help scope your project and then take a look at what do you need as far as support. Do we need to bring in our supporting data and walk through you with that qualification? But we work with people that have projects ready to go too.
100 machines. What type of industries are you hitting?
65% is aerospace and defense. Then it'd be followed by industrial, which is a lot of machinery, equipment replacement parts. We do a lot of parts that they're not manufacturing anymore. Something from an older machine that's a hard to get part. We can produce those, and we might print 1,000 of them so somebody can put them into inventory, versus going back to traditional injection molding and having to print hundreds of thousands of those parts. Other industries that are very large for us are automotive and medical. And I would say medical is probably the one our teams are most passionate about.
Dental, right?
Dental is
Crazy
huge.
too.
Yeah. Surgical guides, that's
Yeah.
a large one for precision. So parts move from the printer, then they go into our post-processing, then they move into finishing.
So this is your new crazy high-level FDM printer?
Correct, yeah. So this is our F3300 machine. It's our latest FDM system, and it has a lot of new technology and new innovation on there, kind of compared to our traditional FDM. So what you're seeing up here with the 4 lights, those are 4 independent tools, and so we can print 4 different materials at a time. One of them is your support material. So if you have any overhangs, we're building up a sacrificial material there. The 3 other ones you can configure with different colors. You can do backup extruders, so if something goes down or a tip clogs, you have redundancy on the system.
When it comes to like FDM, you guys have done it for how many years?
Over 35. So Stratasys invented this technology. Scott Crump was the founder of Stratasys, invented FDM, and that's really what kicked Stratasys off here.
Just for people that don't know, can you explain what FDM actually is?
So FDM is fused deposition modeling. So we're starting with spools of filament here. That gets fed up to the head. We're melting it in the head and extruding it through a tip. So when we're starting with a part, it's a blank tray with a build sheet on top. And then as we build, the tray goes down. As we're adding the layers, the heads stay in the same position. 800 millimeters tall on this. So you end up with a part that's down to about here, and then you're opening your door, pulling it out.
So 12 years ago, when I had one of your guys' printers, and it was amazing. When you look at a machine like this, how much faster is it compared to what it used to be?
It's about 2 times faster than the previous generation of the system there. A lot of that comes from having these multiple heads. We're spending more time printing and less time doing the different operations on there. We're switching tools, we grab a new one, and then we're instantly starting printing. We have linear rails on here, so we can move incredibly quickly. A lot of the improvements are around the reliability of the system. We have bigger spools of material. We have the redundant print heads. We're actively drying the material, so we have the built-in dryers on the system, keeping that material in the optimal condition there. So this is our 450, so it's a smaller version of the 3300. It's the older generation. We open up the top here. This is our actual extrusion head. The filament's coming through this path, coming up from these canisters. So there's spools of filament in there. This is where it gets heated up, and then the plastic gets extruded, and we're building up layer by layer here. So this is our F900. Build chamber dimensions on this that we can do is 3 feet by 2 feet by 3 feet tall. So this is our largest build chamber that we have today.
One thing I noticed, like looking at all the different printers, I mean, the design of the printer, the manufacturing is absolutely stunning. So where do you guys actually manufacture a lot of your printers? I heard it's actually pretty close.
The FDM systems that we've been talking about recently here, those are made in Eden Prairie, so about 5 minutes from the office we're currently at. And that's where we produce a lot of our filament for these systems as well. Our FDM R&D is in this same building, and they're just 1 floor up.
I love that you make it right here in the US. And the filament, you'd think it would be made somewhere else, but you're making it here also. That's awesome.
The quality of the filament is very important, so we want to control that. If there's any issues, we can send our materials team down to production, figure out what those are.
So when you see all of these printers, and a lot of them are working right now, are you running or testing customers' parts, or your own part testing, or what exactly is going on now?
It's a little bit of everything. Here we do marketing samples, we do the customer benchmarks to make sure that their application is going to work before they buy a machine. A handful of different things in this lab.
So if somebody gets a printer from you guys and it goes down, what does the service look like?
We have our own dedicated service technicians. We have people based in the different regions, Germany and Europe, and then Asia offices as well. So we have support techs all around. Something goes wrong, we want to make sure you're back up and running. We're costing you production time if our system is down. We want to make sure you're happy on there.
So this technology is selective absorption fusion. It's a powder bed fusion based technology. So like all 3D printers, this produces a part layer by layer by layer. There's 2 sleds actually filling the build plate. There's a bed of powder, and one head goes over and deposits a material that is sensitive to energy, and the other is the energy source then that fuses that powder in that particular location. We just repeat that process over and over and over again until you get your completed part.
Inside the build chamber, we're at about 160 C. There's a thermal camera that's essentially the brain of the operation. So it's looking at all of those zones and making sure that we're having equal temperature across the build chamber. And so why we keep it at that high of a temperature is we want it right below the melting point. When we were talking about FDM, you think of it as a way of you have a pencil and you need to trace out every cross section with that nozzle. With this, we're doing the entire layer at once. So it doesn't matter how many parts you pack in there. It takes the same amount of time to do that layer. So you can see the feature resolution that we have. We have some different textures that have been applied in there. So you can see the level of detail on that.
Very cool.
So that's how it comes out of the machine. We can do a smoothing operation on it. So that part there has been smooth. So there's vapor smoothing, and then there's a bead blasting smoothing that you can also do with that. And then if you don't like the gray color, we have a dyeing process in there too.
Okay.
So most people, they prefer black.
So just nice and clean.
Right, with additive topology optimization is something that you kind of get for free. It's just all about what your cross section looks like on there.
So our main product is GrabCAD Print for CNC speak. That's our CAM software. A lot of the GrabCAD core tools are around prepping jobs to go into the machine, extracting value from those parts, and then operating those machines in a production floor. Having the machines is great, that's step one, but who's using those machines? So what we want to do is empower those people to solve their own problems with 3D printing. Now we need to fill the pipeline, we need to educate people around an organization to really leverage professional 3D printing to solve problems for their day jobs. That right there is Ultim 1010 actually.
Oh, nice.
Because it's a weld fixture, you don't want it melting. And then another thing we've seen with the lower end materials or printers is you have a clamp like this, but if the plastic is actually flexing instead of the clamp applying force, it kind of defeats the purpose. This is very rigid and high strength material. So I know you know SolidWorks pretty well. Mm-hmm. How long would it take you to design this fixture to hold it and clamp it together?
I don't know, probably a couple hours.
Couple hours, yeah. So this is done in 5 minutes, and design for additive is baked into it. The biggest thing in SolidWorks is, first of all, you'd have to have a model of this clamp, design the attachment features to the clamp, but maybe it's a fixture where you have to assemble it multiple times, so you want some clearance on it. You would have to offset the surfaces in SolidWorks. It's a lot more complicated than just subtracting a body. And so this is tailor-made software to do this exact job. So now you're just compressing that timeline because you can do it yourself in 5 minutes, send it to a printer, and move on.
How complex of geometry and parts can you actually make on that software?
Like I said, this is 5 minutes, but you can go in and do other operations. You can add labels, parts that come in at different angles. So like if you need a lid or something to protect it, you can get pretty complicated with it as well. And then you can always bring this back into CAD after you've done 90% of the work if you really need to do some more manipulation and stuff like that. By November, we're gonna have 11 different apps. So this one is for fixtures. We're gonna have one to create soft jaws, which I think you would be really excited to use.
Yeah, very cool.
Hold complex parts in a vise.
You guys have like tens and tens of thousands of customers. When you actually work with Stratasys, they'll teach you how to design all of it, how to make fixtures and do everything like quick. You teach all your customers exactly what you were just talking about.
Yeah, I mean, that's key for us, whether it's somebody making a part going on an airplane or a fixture like this. How do you create utilization? How do you create demand? And how do people ultimately learn and be able to benefit from the technology?
Very cool, man. Great job. Boom.